Hi, we are still in the bitwise operation series. This time we are going to talk about practical bit games. Objectives of the lesson. We will learn about some basic bit manipulation techniques, extracting one specific bit from a number, counting the number of ones in a binary number, calculating modulo powers of 2 using bit operations, and squeezing many small numbers into the same container. Let's begin with extracting bit value. We have this challenge. We have a number x and we want to obtain bit number k from x. I remind you that the leftmost bit is 0. So if we count beginning from the right hand side, this is bit number 0, 1, 2, 3, 4, 5, 6, 7 for example. Maybe for example we just want to get bit number 7. We don't care about the other bits. A simple solution for this would be to end the number with a special mask. A mask is just some kind of a number that has only a bitwise meaning. It doesn't have any arithmetic meaning. So in our case, we wanted to have bit number 7. We can just compose this binary number, which is all zeros, besides bit number 7, which is 1. 0, 1, 2, 3, 4, 5, 6, 7. This is bit number 7. We don't want to write all those digits, so we can just write it as a hexadecimal number in this form. This number equals this number. And then we use the AND instruction. As a result, we are going to have two options. Either we get this number as a result, or we get the 0 number. It only depends on bit number 7. So if bit number 7 was 1, we get this number. If bit number 7 was 0, we get 0. So we can just AND and then check if we got 0, which is going to be very indicative. It will tell us all the information we need to know about bit number 7. If it is indeed 0, it means that bit 7 is 0. So we have this label and this jump 0, which jumps to this location, this label. So we get here if bit 7 is 0. The other place is here, just right after the jump 0 instruction. And we get here if bit 7 is 1. As we usually structure our if statements, we have this jump here in the end of this part to make sure that we don't just slide to the next part. So this part jumps to the end of this if statement. Another idea for a solution. Recall that the carry flag is a copy of the last bit that was kicked out from the number. So maybe we can use some kind of instruction like row, rotate right. We can just rotate right 8 bits, and we know that the last bit that was kicked out is bit number 7. For example, we can rotate right EAX by 8 locations, 8 positions, and then jump only if there is no carry, which means that bit 7 was 0. If bit 7 was 0, we get here, and if it was 1, we are here. And for the most part, this is very similar to the previous solution, just that we use the carry flag instead of the 0 flag. In addition, because we used the row instruction, the rotate right instruction, we didn't override or deleted any information. So we can recover the original EAX by invoking this instruction later, the rotate left instruction, which gives us the original EAX. Another kind of a question. We have this question: how many set bits or 1 bits are there in some binary number x? This is also known as the population count question. We have, for example, this number, and we want to count the amount of 1 bits inside this number. It's not very hard to see in this example that there are about 5 set bits. These are the set bits inside this number. We want to create some kind of a piece of code that can do this automatically. An example for a solution. We extract every bit from EAX using the AND instruction, and then we sum all the bits. Because bits are only zeros and ones, we can just sum them and then get the amount of bits. In the beginning, we initialize EDX to be 0, and EDX is going to count the amount of 1 bits. And then we move 32 in decimal into ECX. ECX is going to be some kind of a counter, and because we have exactly 32 bits, putting in 32 is a good idea. Now we have a loop. We can see that we have this label, which is the beginning of the loop, and this loop instruction in the end. So we can already see this loop in this piece of code. Now we take EAX, which is somehow the input that we get, the number that we want to count the set bits in. And we first take a copy of this number into EBX because we don't want to ruin our input. We don't want to end some kind of a mask on the input because then the rest of the bits of the inputs will just be gone. It won't be very good. So we first copy EAX into EBX, and now we work with EBX. We end EBX1, which takes the lowest bit inside EBX, and then we add it to EDX. I remind you that EDX is the counter of 1 bit. So if the bit was 1, EDX will actually increase, but if EBX was 0, this instruction will have no effect on EDX. EDX will remain unchanged. Finally, we rotate right EAX to make sure that in the next iteration of the loop, we deal with the next bit in EAX. So this loop is going to sum all the bits inside EAX, which means that it will actually count the amount of 1 bits in the number. Another idea for a solution. We can rotate EAX 32 times, and each time check the carry flag. We know that the carry flag has a copy of the last bit that was kicked outside the boundary of the number. So, just as before, we initialize EDX to be 0, and EDX is going to count the 1 bit. And we also initialize ECX to be 32, which is actually the number of iterations that are going to happen in this loop. Note that here we can see the structure of the code. There is one big loop, and inside of it, there is some kind of an if statement. There is a conditional nested inside this loop. Let's take a better look of what is actually happening. First, we rotate right EAX by 1. Why do we do this? We want to get a copy of the least significant bit inside the carry flag. Next, we use this instruction, jump not carry. The jump is going to be taken only if the bit that was kicked out was 0. So we have this label, bit is 0. Actually, this jump is just about skipping this instruction, the inc edx instruction. So if the bit is 0, we skip this instruction in the middle. However, if the bit that was copied to the carry flag, which is also the low significant bit of EAX, if it was 1, then we actually do this instruction. And as a result, EDX is increased by 1. So this loop actually counts the number of 1s. It goes over every bit. For every bit it checks whether it is 0 or 1. And if it is 1, then the loop increases EDX by 1. In the end of the loop, EDX is going to contain the amount of 1 bits inside the number EAX. Calculating modulo. Another kind of question that happens pretty often. We want to calculate x modulo 2 to the power of k. maybe it could be x modulo 4 or maybe 8. It happens very often. We could use the div instruction, which we have learned about. We know that the div instruction produces two outputs. It produces the quotient and the remainder. So it will work. However, the div instruction is a pretty slow instruction. We haven't spoken much about speed so far. However, this is something that you should probably know. Div is not a very fast instruction. Maybe we can do something else. We can take advantage of the bit structure of the number. We know that the structure of x is something like this. b0 times 2 to the 0 plus b1 times 2 to the first plus b2 times 2 to the second, and so on. This is the usual binary representation. We also know that if we go far enough in this representation, we will get to this element, bm times 2 to the power of m. And we know that 2 to the power of k actually divides this number if m is greater or equal than k. So if we want to get the modulo with respect to 2 to the power of k, it will be enough to just consider the first part of the representation, which means that it is enough to consider the lowest k bits if we want to know the modulo with respect to 2 to the power of k. We don't care about bit number k plus 1. It doesn't affect the modulo. So let's look at some possible pieces of code to calculate this modulo. For example, calculating modulo 4. The solution is very simple. We just AND the number EAX, which has the input, with this number 1, 1 in base 2, which is actually 3. Usually when you write this kind of code, it is a better idea to write 1, 1 in binary than writing 3, because 1, 1 is more readable. When someone is going to read your code, it will be much easier to understand if you write 1, 1b, because then the reader of the code will understand that you actually refer to the bit structure of the number. Another example, which is pretty much the same. AND EAX with this number, which contains how many ones? 1, 2, 3, 4, 5, 6. 6 ones. 6 bits. This example calculates modulo 64. It does EAX modulo 64. I want to remind you that this method only works for calculating modulo with respect to powers of 2. It won't work if you want to calculate modulo 3. Only powers of 2. Data packing. We are going to deal with this challenge. We have two numbers inside AL and BL. AL and BL are not so large. AL is smaller than 2 to the power of 5 and BL is smaller than 2 to the power of 3. So actually AL is not larger than 5 bits and BL is not larger than 3 bits. We want to squeeze those two numbers into DL, which means that we want to squeeze two numbers inside 1 byte. DL is of size 1 byte. And it should be possible because DL is of size 8 bits and we know that AL fits inside 5 bits and BL fits inside 3 bits. So 3 plus 5 is 8. It should be enough. Let's look at a possible solution, and we show you two pieces of code. One for packing and the other one for unpacking. Why? Because we might want to have one part of the program pack those two numbers into DL, and maybe another part of the program will want to unpack those two numbers, so it could actually do some work with those numbers. Let's begin with the packing. The structure that we design is something like this. This is the DL register, which is of size 8 bits, and we want to pack A and B. We just choose the order arbitrarily. We choose that B will reside in the lowest 3 bits, and A will reside in the highest 5 bits. We could swap it if we wanted. This is pretty much an arbitrary decision. We begin with the packing. We want to pack the two numbers which we get as input, AL and BL, and we consider the contents of those two numbers to be A and B, respectively. So first we move AL into BL, then we shift left by 3. To make room for B, we are going to put B inside here. So we first put A inside, then we move it by 3 locations to the left, and then we put B inside. How can we do it? We use the OR instruction. This is pretty much a very simple example. I want to note that instead of this OR instruction, you could also use XOR. I will leave it to you to think about it. This is pretty interesting. Let's look at the unpacking part. We first assume that DL contains this structure. It contains two packed numbers, the number A and number B. It seems like this procedure is a bit longer than the packing. This is kind of mysterious why the unpacking is a bit larger than the packing code. But we can still follow it and understand everything. We begin with making a copy of DL because we don't want to ruin the contents of DL. CL is going to contain the copy. Now we use the AND instruction to take the lowest 3 bits, which are actually B. We just delete everything else inside DL and take only the lowest 3 bits. And then we move it into BL, which means that now BL contains only 3 bits, which represent the number B. The rest of the bits, the highest 5 bits of BL, are going to be 0. Next, we use the copy of DL that we have kept before inside CL, and we shift right by 3, which means that we are going to get A. A will actually move 3 locations to the right, 3 positions to the right, and we will have A from bit 0 to bit 4. Finally, we move the result, CL, into AL, which means that now the lowest 5 bits of AL are going to contain the number A, and the highest 3 bits of AL are going to contain 0. And we successfully unpacked those numbers. Summary of what we've learned. We've seen extracting one specific bit from a number. We've also seen a piece of code that counts the amount of set bits in a given number. We learned how to calculate modulo 2 to the power of k without using the div instruction. And we've seen how to pack two small numbers into one register and how to unpack them. See you next time.